Good morning, afternoon, and evening, folks, and welcome to another edition of Postgres Pulse. We are now on episode 6, and we've made it through the prior 5 episodes by addressing questions and concerns and just overall interest that you have as users in the Postgres community, where it may pertain to anything ranging from performance to stability to general use practices. I'm your host, Jamie Watt, and with me I've got Josh Heyer, our moderator, as well as Vibhor Kumar and Bruce Momsen. This week, we're touching on explain and plan analysis. Understanding explain sometimes requires, well, frankly, some explanation. In fact, the more you dive into it, you realize there's a whole lot more beneath the surface that requires exploration in order to be properly armed. We see a lot of questions about explain, both in our own customer questions and engagements, as well as out on DBA Exchange, PostgreSQL.org, and Stack Overflow. Most are just looking for an answer so they can move on to their next task or goal. So we thought we'd switch things up a little bit and start out with the Q&A this week, rather than going into anything that we see necessarily out on some of the forums we've addressed in the past. In advance of jumping into those questions, I would like to remind everyone, please use the Q&A button to ask a question. Please make sure to stay muted unless you're talking. We will actually go ahead and unmute you while you're posing your question or we're interacting, so that we can speak with you guys as you form your questions. And finally, be civil and please abide by the Postgres Code of Conduct. So that said, Josh, if we could take the first question from our audience, I'd like to jump right in if we could.
Sure. We're answering question found on DBA Stack Exchange, which asks, in essence, explain execution is telling me that an index scan on a 3-column index is using columns 1 and 3. How is this possible when column 2 isn't being used in the query?
That's a good question. Vibhor or Bruce, do you have any thoughts here?
Yeah, I'm just looking into this question. Okay, all right, so you're sharing the screen. Okay, wonderful. Yeah, I think it totally depends on multiple conditions, I would say.
Okay.
Like the way Postgres optimizer works and which path it choose, it depends on that. So you can think about mainly whenever Postgres choose index scan, right? And it filters out the data which it wants, the path will be showing based on 2 conditions. One is that, first of all, index should be smaller, and how quickly it can get the data or less number of rows using a specific index path. So that is called discarding index tuples, which optimizer is trying to scan. And second is based on the row conditions. So in this case, it looks like optimizer must have picked up an index, which is a 3-column index or composite index, and it found less number of rows, right, based on the index scan. And yeah, and that's why it's using, and then it's doing a filtering based on C. So yeah, based on C column. So it looks like it totally, and as I told you, right, totally depends on the stats which is available for the optimizer to look at. And based on the stats, it's trying to find out the optimal way to use optimal plan to use to get the data directly from a disk. It could be possible that the optimizer may choose an index and where it doesn't need to reach out to the rows altogether. It just needs to scan the rows. And after scanning the rows, which is called index only scan, scanning the rows, it can apply the filter and try to find and use that plan to get the data out of disk. So, I mean, I wouldn't be surprised if the optimizer is using a specific path. As I told you, it's a cost-based optimizer. It totally relies on the stats you have, and if the statistics not properly updated, then it may choose a bad plan.
Okay.
So is this only likely to happen when you're at least using the first column in your query? I mean, is there any possibility for the use of an index, a multi-column index, if you're not at least using the first one?
I mean, as I told you, the plan is purely depend on the estimations, row estimation based on the stats. So if it sees multiple indexes, let's say you have a composite index and you have a multiple indexes based on a single individual columns. If the optimizer sees that based on the estimation, fetching the data using the multi-column index or composite index is better than fetching the data based on the individual indexes, then it will definitely go with the multi-column index. There is no hard and fast rule defined that if you have indexes, right, then it will choose a specific index. So yeah, it totally based on the cost or estimation, based on the stats of the tables, right, based on which optimizer decides which plan it has to pick up.
So if a sequential scan was just incredibly expensive, but you had
Yes,
a lightweight index, even if you had to look through every single element in that
it
index,
depends
it
on the
wouldn't scan.
conditions. Yeah. So if you have a predicate condition which you're using, it in which case, let's say there's a column defined, right, and there is no index defined on that, it may go with the sequential scan. In certain cases, if you have indexes and index are pretty much bloated, and the size of index is very, very bigger than the normal table, right? Or let's say if you have a corrupted index too, in that case, it may go with the sequential scan. Bruce, do you have any thoughts?
Well, there's probably two things happening here, two possible things, right? One is if the first column is unique enough, distinct enough, right? Then effectively you can do what's called a skip scan. I know there's certain databases called skip scan where you look up the first value, the first column in the index, and then you spin through the index looking for a match on the third column or fourth column or whatever. So it allows you to effectively look up the first column in the index, and then instead of going to each heap row looking for the third column, you can walk through the index trying to find matches on the third column, right? So that's called a skip scan. We've implemented a couple of years ago, so it's possible that's what's going on. The other thing Gabor mentioned that I hadn't thought of is the idea that this is an index-only scan, which doesn't show here, but it could be potentially another case where you're not you're looking up the third value not because you're trying to restrict on it, but because you don't want to go to the heap at all, and therefore you're going to filter all of the rows that match the first value and remove everything that doesn't match the third value. So that's another possible use of a multi-column index. I've seen people who create multi-column indexes where the first column is unique. That's what include indexes are. If you've ever seen, I think in Postgres 12 we implemented these include columns for indexes, and I remember thinking, what good is this? Like, why would you want, if your first column's already unique, why would you want these other columns, right? And the answer is because you can then do an index-only scan, and therefore pull the other columns off the index without ever having to go to the heap, even though they're not technically part of the uniqueness of the index. That's the weird part, is that you can create an index where some of it's part of the uniqueness and some of it isn't, which is what that include clause is when you create an index. So it could be a skip scan. That would be one case where you'd use that. You wouldn't use the second column, but still use a multi-column index. The first column could be unique enough that you don't even care. You're just going to like, I only got 2 rows and they match column 1, value 1. Because think about it, when you create an index, ABC, well, you might have some values where there's a lot of A's, right? There might be, but you might have some values where there's only a couple A's, right? So you don't even care almost what the other values are because there's only 2 rows in the whole index that have an A equal to 5, right? So that when you're creating an ABC index on a whole table, you're thinking, oh, well, I've got a lot of duplicates and stuff. Well, there might be a bunch of values where the first column is unique enough. And then you can either filter through those before you go to the heap to skim off anything that doesn't match the third or fourth value, or you may be doing an index-only scan in this case. So there's definitely a lot of use to these multi-column indexes. And I don't think there's ever a case where it would use, I understand what Vabor's saying about the cost. There's nothing that says we can't use just the second and third columns of an index, but I don't think the costs would ever come up that would actually happen. I don't think the costing, I think the costing would always prefer a sequential scan of the heap, because the cost of effectively sequential scanning an index because you don't match the first column is going to be always higher, I think, than doing just the sequential scan of the table. Because remember, these indexes have to be 5%, restrictive on the table to even be considered. Much lower value than most people think. Because people think, well, if I can skip 40% of the table or 70% of the table, I should use an index. But no, indexes are incredibly expensive. A lot of random IO, a lot of bouncing around before you even get to your data. Sequential scans are really fast. So you have to be really restricted before an index even costs to be something you consider.
Great, thank you. Go ahead, Josh.
I know this is going off a little bit on a tangent, but I know you touched on this recently in a blog post. The cost of looking up in an index on an SSD or on an NVMe device, does that make any substantial difference in the evaluation between?
Oh, it absolutely
which to use
does.
there?
Yeah, absolutely does. I mean, when you look at the cost, I know there's a lot of math in the random page cost, docs, Postgres docs. Random IO for a magnetic disk is probably 40 times slower, I think, than sequential access for magnetic. For SSDs, it's just slightly, random is just slightly slower, maybe like 2% or 5% or something like that. So what we usually recommend, and I put a blog post out about this last week, I guess, was basically saying that for SSDs, you do see a lot more. You have to adjust the cost. As Vabor said, system doesn't know you have SSDs, so you have to set the random page cost to be probably 1.1, I think is what I recommended in my blog. And once you do that, then again, indexes are going to be a lot less expensive and are going to be a lot more likely to use. So again, for magnetic, it might be in the 5% range, but for SSDs, it may be closer to 20% or 25% restricted before we start using the SSD. Yeah, that's a good point.
So a lot of this might seem like magic to a lot of Postgres users, particularly those that are kind of newer to the platform or newer to some of the underlying principles. Is it worth stepping back and kind of looking at things through a larger lens and saying, these are the things you really need to take into consideration before you start talking about explain analyze, or you start talking about the optimizer? Are there some fundamental understandings that folks should probably dig into before they try and get to this point?
I think the existence of the optimizer itself is something that throws people off. You just send an SQL query that is declarative, from a technical standpoint. Mm-hmm. You're not telling the system what to do. You're saying what data you want, right? And the optimizer is effectively the brains behind that figures out what to do. And most people aren't used to dealing with software like that, right? In almost every application, or if you do stuff in Django or whatever, I mean, you kind of, there's some logic behind the function calls you make, but you don't expect sort of heuristics to be changing you expect the same code path to happen all the time, pretty much.
Right.
No matter what constants you use, pretty much you assume the same behavior, right? And with the optimizer, one of the reasons SQL is still so popular after 70, 50, what is it? I guess we're 50 years or 49 years in here, is because that heuristic that allows you to just send a request and figure out, hey, this data has this shape. The optimizers figure out this data has this shape, this constant is this restrictive, these indexes exist today, they may not exist tomorrow, right? And then effectively live figuring all that out. Most people just don't even understand that's there. They're just blindly sending queries, which in most cases is fine, frankly. Most systems are not being pounded, with 15, a load average of 15. Most systems are idle. They're just kind of sitting there, kind of very leisurely sending data back to users. And in most of those cases, it doesn't matter. But when you start doing data warehouse, when you start pounding the system and really pushing a lot of data through there and a lot of requests, then you got to start worrying about, okay, what indexes do I need? That's probably your first step is to figure out, am I missing indexes? Because most people don't even put any indexes in, right? Or they put too many, which is another problem. And then you have to look at the cost, right? Am I using SSDs? Are my shared buffers right? Am I using workmem properly? Those are the three ones we see. Typically, people are going to be, do you have effective cache size set to reflect how much shared kernel buffers you have? And you kind of set those 5 basic things, throw some indexes in there, and normally people are fine. But then there's that top percent who's going to go in and look at explain plans and run PG stat statements and PG Badger, start to look for slow queries, right? These are the professionals who really want to get the most out of their system. The entire organization is relying on optimal performance from this thing, and cutting a couple seconds or minutes out of a query, makes millions of dollar difference sometimes. In those cases, that's when you start pulling out your tools. You start looking at putting SSDs for your indexes. You start, figuring out what your cache hit ratio is. You look at PG stat statements, PG Badger. You start looking at queries to figure out, is the optimizer doing exactly what I want it to do? Can I make it better? Can I increase statistics? Can I create, a special type of index? And there's always going to be people who are going to be pushing those envelopes, and the tools are there, right? You just need to stop and take the time. I think the real challenge is to figure out, is it worth it, right? Is it worth my time to figure all this out?
Right.
And it may be, it may not be, right? Depending on what your tolerance is for performance, how important that data is, and then how many people are impacted by improvements. Really spending too much time can be a problem, but then spending no time also can probably not be a good idea.
Hardest optimization cost is on your own time.
Yeah. I'm the type of person
Maybe PG-14 y'all can implement an optimizer that schedules my day for me. That'd be
PG formatter for your life.
Yeah, it's hard to know where to invest your time. I totally agree.
Yeah, it's hard to know, but explain at least gives you some way to show you the cost and which part of the query is taking what amount of time, right? And focusing in those areas would really help you. So for example, if you're running some complex query, then explain would be able to tell you which join is taking so much time, right? And by looking into the join and table, you can decide whether you need indexes or you need to analyze on the table to update the statistics, right? So yeah, so I mean, in my point of view, explain is a really nice tool which gives you visibility exactly how the optimizer is going to use a plan to get the data, and based on that plan and performing some analysis based on the cost would help you to tune the queries. I can give you a very interesting example of my past experience, right? Where a person was using the in clause, and in the end there was a subquery, and that was becoming very expensive for getting the data, right? Because in the set query was putting some where condition, and the number of rows were returned in the subquery was pretty high, and yeah, due to which the cost was pretty high too. So we switched from in to exist clause. That actually really helped to optimize the query altogether. So you can think about, we got 10 times better performance versus exist.
And you picked up on this using explain?
Yes,
yeah.
Based on the explained cost. So yeah, so it really helps.
Vibhor picked up on it because he had all the knowledge of what all those joint types are
Correct.
and how
Yeah.
they interact with everything. And he knew the random page calls was set up right. He knew
Mhm.
probably shared buffers was set up right. And he knew the indexes he needed were probably there. So it's a lot. The explain itself is useless, honestly, unless you have a background of understanding how to understand, understanding that the system, the stuff that all that explained data relies on is accurate, right? And then understanding the join types and how additional indexes would affect those join types and how different types. So there's just so much in that explain that isn't there. It's just some numbers and some names and some terms.
Right.
You can kind of look, okay, where do I have misestimation? But again, you have to understand how the statistics system works. So,
So this all sounds really headachy, and we got a
it
question
really,
that's popped up here from our buddy Richard Yen that kind of might be relevant. You want to take that?
What is the question?
Richard, if you want to go ahead and unmute yourself, you should be able to ask that.
Hello, can you guys hear me?
Yeah, we can
Yeah.
hear you. Morning.
Oh, cool. Yeah, I was wondering, since we've been talking about random page costs and tuning, is there some programmatic or formulaic way to tune that? I know a lot of it has been just kind of it's anecdotal, I guess. So, is there any formula that we can rely on or develop for that?
you know, there is and there isn't.
Yeah.
We could have, we have PG Test F Sync, which does a little bit of, it doesn't go random, but it does some performance numbers of how quickly we can push data through the system. And we could write, and there's another program, a Perl program that allows you to test if F Sync is durable and a whole bunch of other stuff. But and we could test. There's IO zone, I think. Is that what it's called, Vibor?
The I concurrency you're talking about?
No, there's a utility that does random and sequential perform. I don't remember what I thought it was called. IO
Yeah.
years ago, that's what it was called. And it will give you the actual numbers for random and sequential page costs, Richard. However, the problem is that when Postgres is planning a query, it doesn't know if the data is going to be coming from storage or whether it's going to be coming from the kernel cache or whether it's going to be coming from shared buffers. So if you read random page cost in the Postgres docs, it says that probably sequential versus magnetic is 40 times slower. I already talked about this. However, the actual default for random page cost for magnetic is 4, not 40. And the reason it's 4 and not 40 is and there's some sort of math in that example, is I think we assume like 80% or 90% of the IO requests are going to come from shared buffers, not from the storage, right? So even though if you could tell me exactly what the number is, you still have this fudge factor of trying to figure out, okay, I know what the difference is in my storage, but what difference is it? What percentage is going to go to storage and what percentage is not going to go to storage? And even if you knew that today, you don't know that tomorrow. You don't even know that 5 minutes from now, right? So the bottom line is that this whole costing of queries thing is incredibly sloppy and incredibly just sort of shoot from the hip. And you would think that's just terrible. But again, those statistics numbers are really only used to choose a plan. They're not used, you're still going to get the same result no matter what, right? And it only has to be good enough so it chooses the better plan versus the not better plan. And even if it chooses a not better plan, is that not better plan significantly slower than the absolute best plan that we could get, right? Which is what the genetic query optimizer does, which I just blogged about today, which tries a bunch of random plans, doesn't get the best plan, but gets it good enough and fast enough that you don't care. So the bottom line is, yes, we could get those numbers, but the answer is that when we're running in the optimizer, we don't know what's in shared buffers. We don't know we're going to have to fetch. So we're just kind of slopping a number around and hoping we get a good plan. And in, almost every case we do. But there are probably some we don't. And there's really not a whole lot we can do except for trying to improve the numbers, getting those numbers close is about all we need. We don't need exact there.
Yeah. And even if you have tuned those costs, right, and the optimizer doesn't know the distribution of a data on a specific table, it may pick up a wrong plan based on those costs, right? So again, these are two things: cost, which Bruce just explained you, and there is a statistics about a specific table that is also plays a major role. And the statistics tells the optimizer, helps the optimizer to understand which index it can pick up to to get the less number of rows for specific conditions. So anything which is filtering out the data which you are trying to get it from a disk, right, is really help to pick up a plan which an optimizer can use, the executor can use, right? So those are also important things. So statistics is a key thing. For cost calculation, I'm not sure. Is your question is around the cost calculation or how the optimizer calculate the cost? If your question is around that, there is a specific formula which optimizer uses, right? That is number of block into sequential cost or random page cost, whatever it is, right? And then it adds up into the number of records into the CPU cost. Again, you're calculating this block and CPU cost is of course defined by you, by the user based on the system, but number of blocks which you're calculating is again a rough estimation based on the stats which you have collected, because when you run the analyze command and then analyze command goes and update those statistics into the catalog table, and optimizer uses those numbers to come up with some cost of each plan, and anything which is low cost, optimizer is going to pick up that for the executor.
Yeah, but it's true. Even the column statistics are estimates based on random sampling, right?
Yeah.
And then the random page cost is estimate based on what type of hardware we think you have,
Correct.
how much we think is going to come from memory versus storage, and then when we do a join, we also never quite sure how many rows are coming out of that join, right?
Yeah.
Because we don't really have cross table statistics to know these are going to join 1-to-1, these are going to join 2-to-1, these are going to join 0.5-to-1 or 0.1-to-1. We don't know. Okay. And then we go into, well, okay, depending on how much coin out, then we have to figure out which join type to use, right? Mm-hmm. And then there's stuff that goes above that happens. So almost everything, unfortunately, related to the optimizer is this fudge factor kind of a process, because the data is changing all the time. The absolute numbers are probably not that useful and are expensive or require a lot of locking to determine. So this is, and it's not Postgres' fault. This is the way all of the relational systems work. Usually in 98% of the cases, the best plan is just going to be chosen because everything else is just going to appear so bad. It just kind of naturally just goes in that direction. Yeah. Or there may
what I'm hearing is you're aiming for essentially all these estimates: disk cost, the statistics. You're aiming to be in the right order of magnitude.
Yeah.
But trying to get any closer than that is inordinately difficult and kind of useless because you're going to have so many other factors coming in by the time you're all said and done.
Right. And plus you have time requirements of how quickly you want to spend planning the query versus executing. If the planning takes longer than the time I'm going to save picking the best plan to execute, I've lost, which is where the genetic query optimizer comes in. So you see, you've got these.
Man, we're gonna have to break that one out for another.
Right. You've got these constraints all over you: time, speed, locking, and you just kind of throw up your hands and say, let's just get it close. Sometimes the difference between the best plan and the second best plan is minimal. And it works. It works, and proof's in the pudding. So even though you'd think there'd be so much misestimation that it would never work sometimes.
So it's kind of like the old celestial problem of estimating within a system where any given planetary body is at any point in time, right? The goal is to be close enough, right? You want to be close enough such that it's actually meaningful and not spend so much time on determining what close enough is that you lose the value altogether.
Right, because it does not affect the result. The result's
Mhm.
always going to be the same, no matter what plan you choose. That's, I guess, my bottom line. No matter
Right.
what the optimizer does, even if it's got bad stats, it's always going to give you the same result. The only question is if it can do it as quick as possible.
Got it. Well, that's a great conversation. Appreciate the question from yourself, Richard. And actually, Richard had provided the blog last week as part of the Pulse sessions, and he goes through a fairly lengthy explanation, but valuable, associated to situations where people run into problems with a specific query, and how by looking at explain, analyze, you can kind of walk through what the cause of it was, and then kind of walk through a couple of things that we've talked through so far today. The different types of joins, different type of scans, what are the different factors that weigh into, once you do have all of that understanding on the background of Postgres and the various functions, what value you can use or derive from using explain analyze as a tool in your bag. All right, well, we've come to the end of another session, and I appreciate everyone's in attendance today. Again, thank you, Richard, for joining and throwing that question in there. I think that provided some good value there. So without further ado, I will let everyone get about their days, afternoons, evenings, mornings, and thanks everyone for joining. Take care.
Thanks, Jamie.
Thank you.
So long.